Hello, my name is Gabrielle Hollaender, to number 10623-554. I'm going to be talking about the GDC video that I watched. So the GDC video that I watched is a 2013 GDC video from GDC 2013 in Europe, and it is by Michael Drobin. Basically, what he was covering was advanced material rendering, so I'm going to go over what he was talking about now. So, talking about advanced rendering, he talked about first the simple terms that we already started to get aware of, so using BRDF, parallax mapping, alpha blending, and Q mapping. And here I just have a little included of just an example of that. So the issue that he started to bring up was that with the deferred architecture, our material rendering would get too tricky. So the issues that he noted specifically is that with deferred shading, we need to have a uniform BRDF across all materials during our shading pass. We need one geometry pass, but having a huge G buffer will definitely hurt our bandwidth, and more materials will hurt the speed. However, then he goes on into talking about some techniques. So first techniques that he talked about was the light PrePass. So it uses a lighter G buffer with normal and Z, and then does the material pass, which deals with individual meshes and custom materials. So instead of just having the same materials across the board, all of materials would also be done within our buffers. So here's also an image of basically what that PrePass would look like. Moving right along, then he went on into jittering. So jittering, as noted here, is sampling the pattern to cover noise by rotating disk offset. If we were going to actually look at it in a game, what it would look like would be if we were to look at a shadow and we would see that it's a little fuzzy. This fuzziness is brought on by jittering. So what you need, though, is a good offset distribution table, and this is done using a rotating disk offset. So we are able to move these points around in order to get a better material. So what it's done is it randomized the normal vec n, and then is sampled based off this offset. So linear sampling is also important because we need our exact pixel position. Without this exact pixel position, this is when we can start having issues with the rotating disk offset, and that could lead to some really wacky looking materials that we have on there. Predominantly in the shader, or when this is being used, it uses a flow force sample, it has an index, and also takes into consideration a flow jitter distance. And with this flow jitter distance, it would be calculated as well. Afterwards, he moved more into talking about the different material types that we have and that you could do within our material buffer or material pass. So there's transparency that would kill off pixels within our shader and basically alternates on these patterns depending on the transparency value. So you could have, for instance, an array that has each pixel blanked out at a certain distance, and depending on the patterns that you want to go through, it would change how it looks. So basically you would use a custom edge detection, so it finds edges between the pixels in order to ensure gaps, because if there are no gaps, that's when we would have too many pixels killed off and we would have our things looking weird. Again, another image of just transparency, it's what it starts to look like. So there is full transparency that uses the full eye vector in the project to the back buffer and uses fake real-time reflection. It's supposed to give the air of that we actually have glass within our game while not actually being glass. An example here was with the monkeys that have been applied full transparency and look very glass-like with color applied. Semi-transparent is a bit different since it still does deferred rendering, but with a single transparency. The single transparency instead of multiple transparencies is what makes a difference and also allows it to still have like an actual full look to it. After that, there is then translucent. So translucent only allows light to pass diffusely and is done through our material volume. Here you can see that basically we have them here, but it has no contrast and it's just being diffused outward. It's not going anywhere else. It's not being reflected. So that's how you would get a translucent material type. All of these, though, are still reliant on the shader going in between these patterns and killing off the pixels depending on basically what you want. Afterwards, once he was done talking about the material types, he went more in depth in things that would be more applicable to our games. So, actual skin rendering. Skin rendering uses complex light interactions with diffuse and specular, so things that we're already using in our shader. So this is done through different layers of rendering in order to get a complete skin render. So you would first have your normal layer of skin, then you can have shadow, then you can have oily layers. Basically, however you would like to layer the look of the face would be how you'd be doing your skin rendering. But predominantly, if we want a more natural look and our skin to look more realistic, the oily layer would use a specular reflectance, and then it's dielectric and reflects unaltered light. So for instance, if you're looking at this image here, we have a normal image here that has no light being taken into consideration, but here we can see just a big white spot that we can see is reflected. It mimics basically when our skin gets oily and we would be in front of a light. We can usually see that our skin is able to reflect that. However, in games, since we can't perfectly replicate that, this is one way to do so. The shader calculations deals with specular, so power using our NH, small lobe, and then specular plus equals the big lobe. So that's how we would have different areas as well. But it's not only that. So it is also responsible for diffuse light scattering. Our light waves travel and use a diffuse profile. Depending on what subsurface or subspace that you are wanting to be used, our diffusion profile can change. Obviously, it changes depending on the look or feel that you are going for your game. So these profiles need to be made by the sum of weighted Gaussians. So here we can see a table of weighted Gaussians as well as the graph that graphs it. So this would be used in screen subspace during our material pass and then applied. So the DDX and the DDY for our sampling radius and masking must only be applied to our skin region because, again, this could warp. But otherwise, it follows this profile in order to understand the specific weights of where exactly light is being diffused onto the face. So having that sharper shadow or having a sharper look. And that's how we would get better advanced skin rendering with deferred lighting or deferred architecture applied to our project. Next, he talked about hair rendering, so using alpha-tested quads with transparency, which would take into consideration all the different gaps that we would have in hair, so having hair strands or things like that. Because of how fine it is and not wanting to overtask our GPU, we have to make sure that this is well efficient. This also used an advanced isotropic specular, so it follows it also follows our geometric tangent and uses a direction texture map. We need to render the polygon soup and then render again for deferred lighting. So basically, when we're dealing with our isotropic, it's a specific way that it deals with the specular. The way that it balances out allows it to be more fractured and mesh better with our hair. Another example where this is also used is when you're rendering sand as well. Because of how fine it is, it has to have a specific specular and use the specific specular in order to give us that crisp and correct light reflection that we want here. Lastly, what he finished talking about was water rendering. So how we need wave creation, propagation, and interaction. So this would be done within our vertex shader, and this would be rendered as a tessellated mesh with more triangles in order to obviously give it a sharper look. Our foam particles are generated based off the wave crest and amplitude, and the function that is predominant within this shader in order to render is the Gertzner function. So this basically mimics how water propagates and its traits, and our normal tangents are also based off of this as well. For the light, the extinction is similarly based to realized light absorption. So the calculation would obviously alter, and you would have to look more into how exactly light is reflected in those values, because we wanted to, for whatever instance that we would like to do it, this is as close to real life as we can get. So our light needs to be correspondent and altered in order to give it the best realism or best immersion that we can get with water. But this is the end. That was the end of the video. This is about it was about an hour long, and here's the link here. Thank you so much.